frequencies. And so we're going to have a grid that is first described at a very low resolution, and then details will be filled in at a higher resolution and so forth in a multi-resolution hierarchy with K levels. And each of the levels is represented by an implicit function that stores that the implicit function that it produces isn't f of xyz, it's the residual of f of xyz with respect to the output of the previous level. So like a Laplacian pyramid. So in the picture on the right, this is just from standard image stuff. There's the top level here is the very low res color image. And then what level 2 produces is, if I had upscaled this level 3 things, what's the residual I need to add in order to get an image of that resolution, and all the way down. And it's a pyramid of these things. That's a Laplacian pyramid. So we're going to have a Laplacian pyramid where instead of storing the images, we're going to have an implicit function for each of these things, and in 3D. So how does that work? So a very simple example of that would be if I had a 2-level hierarchy. Of course, we can have more. Level 0 here is going to store some sort of blurry version of the base shape, and then level 1 is going to have different latent codes for grid cells at a factor of 2, a power of 2 greater number, smaller regions. So this, there'd be 8 of them for 3D or 4 of them for 2D. Each of them is going to have a decoder the same as level 0 did, but instead of producing a prediction of what the f of xyz is, it's going to produce the residual with respect to that. So if I add a value here plus a value in level 0, then that's going to be the actual f of xyz. So we're going to sum these things across levels to produce the actual f of xyz. The advantage of representing things that way, like an Laplacian pyramid, is that if the network produces 0, then that means the previous level's function was high enough resolution. So when we get a function that smooth areas of the shapes, or areas that are don't have high frequencies, it's producing 0 is always a safe thing to do for the network, to produce something that's a smooth version that doesn't add frequencies at this level. And so that's a very strong prior for a network to be able to take advantage of. This is a complicated diagram that shows things in more detail. The important things here, I guess, are that there is a decoder, these gray squares, separately for each level, and that the regions of space that each of these decoders consider is smaller and smaller and smaller as you go across the hierarchy. And the sum of these is the actual f of xyz that is produced. And our goal here is to reproduce the sign distance function. And so this is trained by producing a function that matches the sign distance function. This can be trained either as an encoder, decoder, or an autoencoder. So those 2 previous things that I talked about used encoders to produce our latent codes. And therefore, we're not as suited for some applications where the input was very, very sparse or very, very partial, whereas this can be trained both as an encoder, decoder, and an autoencoder. So at training time, both are trained with an encoder, decoder, but at test time or inference time, this method on the bottom right here can be optimized so that given an input, you can optimize the latent code that best describes that input given your decoder. And that's very helpful when you have a very partial observation. And so you're saying, okay, I want to do my best to stay within the shape space, but still match the part that I did observe. And so that's a much more robust way to do completion. One of the ways that we train the multi-resolution implicit grids is to drop out particular latent codes so that the network learns to do completion and learns about how to smoothly interpolate the different functions when data is missing. And so that helps us have a more robust shape space and be able to do completion at test time. Okay, so some experimental results with this. We experiment with auto-encoding accuracy. This is a similar kind of experiment that I've been showing you before, where this does even better than LDIF. The rightmost row is the multi-resolution implicit grids, and the LDIF is what I just described in the previous thing. SIF is again LDIF, but without the implicit local functions, just the Gaussians themselves, and ArcNet was the state of the art prior to all this. It also generalizes well. The cool thing here is that the coarse level can produce a kind of gross shape, but then the networks that are at level 1, 2, 3, the finer levels, those are producing residuals that look at what was in the previous level and say, what do I need to add to that? And that's actually quite generalizable. If I see a flat area in the coarse level, I might say, okay, in my experience, if something was flat, it should stay flat. But if I see something that's kind of almost like a corner, then in my experience, I need to add a residual that makes it a sharper corner or things like that. So the higher levels actually have strong priors for how they need to super res, basically the level above them. And so the generalizability of that is quite high. As far as efficiency, similar story. Here, there's a spectrum of methods that we could use here, depending on how many levels we have in a hierarchy. The bottom pictures show some example reconstructions from auto decoding, and the plots show how many bytes that you have in the representation relative to other methods at different and their accuracies. And essentially, we're as good as or better than all methods at some point in that spectrum, at every point in that spectrum. Okay, and then we also can do things like super resolution, because again, the decoders for levels 1, 2, 3, 4, the higher levels are all trained on data that is high resolution. And so if you give it low resolution data, they already have learned how to add details to low resolution. And so we can apply that to provide super resolution. You can give it a very, very coarse input and still produce a high res output that just following the priors for how to super res things. And so that's a really cool application of this. And then again, if we do depth completion, the results are both, are advantageous generally. This is a plot for the horizontal axis is how far you are from the ground truth, and this is the percentage of the predicted points. You want to be higher on this plot. So MDIF is the one I'm just describing, the multi-resolution deep implicit functions. The green curve here is LDIF, the local deep implicit functions that I just described in the previous section, which apparently does better on situations where the answer is really bad. So when the answer is good, like the parts that you do see or something like that, MDIF is better, but LDIF makes less catastrophic errors than MDIF is in the places where it gets it wrong. Okay, and depth completion is actually not such an easy thing to evaluate, because having a distance threshold to a ground truth is difficult when there are many plausible completions. Like, so if this is the observation, the thing on the left, what the other side should look at, it's really hard to evaluate that with just how far are you from the ground truth, because there are many possible completions. And so we actually did a user study where we asked people which of these two predictions is a better reconstruction. So the top thing is what the observation is, and the bottom thing is two possible completions. We ask people which of those is better. And what we find is that if we compare the last two methods I described, LDIF is the one with a mixture of Gaussians, and MDIF is the multi-resolution, that the multi-resolution is a little bit better. Okay, so I have described 3 different methods for combining explicit decompositions of geometry with implicit functions to produce learned implicit functions that have, favorable properties. Um, the to summarize, these representations not only encode the shape, but because there's an explicit aspect to them, they also encode an interpretable structure. In the case of the multi-resolution, it's into frequencies. In the case of the mixture of Gaussians, it's these where the blobs are and how they're consistent across different shapes and how they basically decompose into semantic parts. That's not demonstrated, but that's just tends to happen. So they're valuable beyond just encoding the shape. Because they leverage priors, they can complete unobserved parts of surfaces better than explicit representations. In comparison to pure implicit functions like ocnet and things like that, they represent shapes more accurately and more efficiently because they are decompose the implicit function, the learned decoder into local regions and therefore have smaller shape spaces, which helps them generalize to novel spaces and scale to arbitrary complex shapes and scenes because you can add more and more frequencies, or you can add more and more Gaussians, or you can add more and more grid cells. With regards to where to go from here, there's a wide variety of things that can be investigated. And frankly, many people are investigating variants of this. There's probably 100 papers that are like this, in this space now. Some of the questions you might ask is what other implicit functions could you evaluate and leverage these same ideas? An obvious example of something worth investigating is this NERF, which is neural radiance fields. This is something that I'm sure you're aware of, came out at ECCV 2020, that is able to reconstruct novel views by learning a NERF MLP. The purple box here is an MLP that takes in X, Y, Z, phi, theta. So just basically array and outputs color and density, and then use volumetric rendering to resynthesize a new view. And it's kind of amazing how well it can learn the 3D geometry of a shape from multiple views, training an MLP like this. Others have looked at various ways of combining explicit decompositions and NERF, so neural volumes or neural textures or neural sparse voxel fields. And many of the ideas of those methods, that are quite recent, are similar to the ones that I was describing. But I'm sure there's a variety of other things that could be done. And another thing you could ask is what decompositions make sense. I describe decompositions into grids, mixtures of Gaussians, and frequencies of a multi-res hierarchy. But you could decompose into objects or into temporal things or materials, or there's just a million different ways you could decompose your scene. You could decompose based on illumination, reflectance, and shape. Anyway, there's lots of different decompositions you could do, and I think all of them would benefit from the same kinds of ideas here of each of the local functions that you have to produce are going to be simpler and more consistent. So if you decompose into objects, now your implicit function has to describe just cars in this example, whereas before it was like arbitrary combinations of objects is what they had described before. So investigating different decompositions, I think, is going to be something that people do for quite some time. And then other applications is another thing where implicit functions are not just about describing shapes. They could be anything. They could be describing affordances, which is like how a robot has to pick up an object. In this work that I'm showing you on the right, that's something from the Amazon Robotics Challenge, where the network predicts a grid of locations that would be good to grasp at. And they're stored currently as an explicit, grid, but it could be an implicit function as well. Or you could predict physical properties, like what is the elasticity of this object given an observation.